Hello. Today we're going to talk about quantum random number generation on a mobile phone. This paper was done by four physicists at University of Geneva at Switzerland. The security of cryptographic protocols rely on the generation of high-quality random numbers, but high-quality random numbers are very hard to produce and cannot be generated by deterministic algorithms. To circumvent this problem, we can introduce an external entropy source. In this paper, the authors have proposed a random number generation algorithm using surrounding lights as an entropy source. Each light source emits photons at random times, and it is impossible to perfectly define the number of photons emitted per unit time. This is a quantum event. In old days, counting photons needed bulky and expensive hardware. But now our cell phone cameras are strong enough to calculate the number of incoming photons. So the author proposed this novel idea to generate a quantum random numbers using our regular cell phone camera as a photon detector. So at the end of the presentation, we hope you'd be as fascinated and as confused as we were while implementing this paper. So this quantum random number generation has two parts. The first one is the evaluation of quantum entropy, and the second part is the extraction of random number from that quantum entropy. So it all starts with finding a good camera, and we'll explain later what a good camera is. So it all starts with photons hitting the camera sensor. Those photons are converted into electrons, and those electrons are converted to unique digital codes. And finally we get our quantum noise. If n bar is the mean number of photons, we use the equation to find the quantum entropy. If we have a very large number of incoming photons, for example, if your camera is facing a very large light source, very bright light source, then you use the second equation, and in our implementation we use the second one. After generating quantum noise, we add some technical noise to it, and a technical noise can be an thermal noise of the device, leakage current, or camera readout noise. And when we add the quantum noise and the technical noise linearly, we get quantum entropy, and we are naming it XQ. So now we are going to encode quantum entropy over B bits, where XQ by B is less than 1. On the paper it says the measured quantum entropy is encoded over B bits, where X by Q by B is less than 1 with unique quantum entropy per bit. And I was a little confused, so I had my own interpretation. So what I did is that I created a vector of 2000 elements, and each element has XQ by B into 100% chance to be 1, otherwise 0. So I generated a vector like this. So that's the end of part 1, and in part 2 we're going to use an extractor to generate a random number from that vector. So we'll multiply the vector with a randomly distributed pre-generated constant matrix of dimension 2000 with 2000 row and 500 column. And we'll multiply the vector and the matrix, and the result will be in mod 2. And finally we'll get a string of 500 bit, and that's the quantum random number. In this paper, author used two cameras to demonstrate their algorithm. The first camera is ATIK383L, and the second camera is Nokia N9. The first one is a commercial astronomy monochrome CCD camera, and the second one is a very generic CMOS sensor. before they used these cameras in the experiment, they had to make sure that these cameras meet the specification. They had to check for the noise level that's already there in the camera. They also had to check for the saturation, which means if the incoming photon count crosses a certain threshold, the image will start to saturate. The ATIK383L has a very high saturation threshold, which is 20,000 photons, but the Nokia N9 has a saturation threshold of only 500 photons. So in the experiment, they used the light source was 15,000 photons strong for the ATIK camera and 410 photons strong for the Nokia N9 camera. So in the part 1, when we were evaluating the quantum entropy, the quantum entropy for ATIK383L was 8.9, and again we used the equation we mentioned earlier. And the quantum entropy 8.9 was encoded over 16 bits, resulting in an average entropy per output bit of 0.56 for the CCD sensor. And in case of Nokia 9, for 10 photons, quantum entropy was 6.4, and this 6.4 quantum entropy was encoded over 10 bits, resulting in an average entropy per output bit of -64 for the CMOS sensor. And again, there wasn't an explanation why they chose 16 bit for the ATIK camera and 10 bits for the Nokia camera. And part 2 is the extraction of the random number from the quantum entropy. So they generated the vector of 2000 elements, and they multiplied the vector generated from quantum entropy with the pre-calculated matrix, and the multiplication of this vector and this matrix was the quantum random number. Now we are going to show you our implementation of this quantum random number generation algorithm. So we've implemented it in Java. When you run the program, it will give you some notes about how much incoming photon should you use as an input, because if it goes too low, that means there is no light on the scene, or the camera is absolutely noise free, which is not possible in real life. So to simulate the example explained in the paper, I will go with the 15,000 photon count for the ATIK383L camera. If you press enter, first it shows you the camera parameters that it is using, and after that it shows you the calculated quantum entropy, and then it calculates the vector from the quantum entropy, and the vector is 2000 bit long, and finally it generates a pre-calculated matrix and multiply the vector with that matrix and generates the 500 bit long quantum random number. And this 500 bit long number is the final output. So what is the strength of this algorithm? This is directly quoted from the paper, and it says, if everybody on Earth used such a device constantly at 1 gigabit per second, it would take 10 to the power 80 times the age of this universe for one to notice a deviation from a perfectly random bit stream. So what is the weakness of this algorithm? Well, there are several. One is the possibility of a dead pixel in the sensor. Second is the correlation between the pixel values and a given digital code. If you remember, we are translating the photon into electrons, and the electrons are being encoded in a in digital code. The final problem is the slowness. I tried to implement it using my webcam, but I have to calculate the random number 30 times per frame, but the performance wasn't reasonable. So as an alternate, one proposition is to use FPGA or embedded the algorithm directly to this image sensor chip. So why should we care? At the beginning we said we need a high quality random number generator for better security, and this system guarantees a high quality random number. Quantum computers are still far from regular use, but the usages of quantum random numbers are bound to have an important impact on information security. Thank you, and that's the end of our presentation.